If you've ever thought about how traffic in a modern, a huge network figures out the absolute fastest path to its destination without a human telling it every single step, then you're thinking about dynamic routing. And today, we're doing a deep dive into the backbone of so much of enterprise networking. Open shortest path first, or OSPF.
That's right. And when you look at the source material we have, the documentation, the foundational text, this becomes clear so fast that manual static routing just doesn't scale.
Not at all.
Not for any network with real complexity. Routers have to, they have to cooperatively and automatically learn about every single subnet. So our mission for you today is to really unpack OSPF.
The dominant protocol, really.
Oh, absolutely. The dominant interior gateway protocol. We're going to compare it to older things like RIP and then break down the specific logic that makes OSPF so powerful. You know, how its neighbors form, how they sync up their databases, and then how they use math to calculate that perfect path every time.
Okay, but before we jump into the algorithms, there's one piece of terminology we have to clarify. The sources really emphasize this, and it trips up a lot of people.
I know exactly the one you mean.
The difference between a routing protocol and a routed protocol.
Yes. They sound the same, but they're completely different jobs. A routing protocol, which is what OSPF is, that's the set of rules, the messages, the algorithms. It's the network intelligence.
So it's the process that builds the MAC.
It builds the map. It figures out the best path.
Okay, so if the routing protocol builds the map, what actually travels on the map?
That's the routed protocol. That's the actual traffic itself. It's the protocol that defines the packets that a router can forward. And, in pretty much every modern case, that's going to be IPv4 or IPv6.
Simple as that. OSPF figures out where to go, and IP is the actual data traveling on that route.
You got it. You need the map, which is OSPF, to define the road network. But the CAR, the IP packet, is what actually moves along it.
Perfect. So with that foundation, let's look at the jobs that all of these dynamic protocols have to do. OSPF, EIGRP, even the old ones like RIP.
Right. There are 4 core functions they all share.
It's interesting that the goal is always the same, even if the methods are completely different. So what are those for?
First, they have to learn routing information from their direct neighbors. Second, they need to be able to advertise that information onward to their neighbors.
Okay, learn and advertise.
And third, if a router hears about the same destination from, say, 3 different paths, it has to have a way to select the best route. And it does that based on a metric.
And the fourth one, I'm guessing this is the most critical one, especially when things are constantly failing in a big network.
It really is. The fourth function is the ability to react rapidly to topology changes. This whole process has a name: convergence. Convergence is just how fast the whole network of routers realizes a link has failed, recalculates all the paths, and installs the new best routes. Slow convergence, well, that means lost traffic.
And downtime.
Yeah.
Which nobody wants.
Exactly. Which is why modern protocols are built for speed.
And to understand where OSPF and its peers even operate, we have to talk about how the internet itself is organized. Everything lives inside what's called an autonomous system, or an AS.
Correct. An AS is basically one large network under a single company's control, an enterprise, a university, an ISP, whatever it is. And every single AS gets a unique number, an ASN, from organizations like INA.
So that single administrative boundary, the AS,
Yeah.
that's what creates the big split between the 2 types of routing protocols we use.
Right. IGPs and EGPs.
Interior gateway protocols and exterior gateway protocols.
Exactly. So we use interior gateway protocols, the IGPs, for all the routing that happens inside one of those autonomous systems.
So that's our OSPF, EIGRP, RIP.
Yep. They handle the traffic flowing within the company's network.
But the internet is made of, what, millions of these different ASNs? So if my company's network needs to talk to, say, my cloud provider's network, that's a different AS. What handles that?
That's where you need an exterior gateway protocol, an EGP. That's the protocol that stitches the entire global internet together, communicating routes between the different ASNs.
And there's really only one of those that matters today, right?
That's the key fact from the sources. Today, the Border Gateway Protocol, BGP, is the one and only EGP in use. So IGPs are your internal guides, and BGP is the global connector.
So if the IGP's job is to manage that internal flow, the next question is, how? How does it decide where the flow goes? If a router has 10 ways to get somewhere, how does it pick the best one? And that brings us to the great metric showdown.
This is really where you see the evolution of network intelligence. Historically, we can kind of categorize IGPs into three branches based on their logic.
We started with the original distance vector protocols back in the 80s, right? Mostly RIP. Simple, but slow.
Very slow, and sometimes it made bad decisions. Then you had a kind of transition protocol, the advanced distance vector approach, which is EIGRP.
Cisco's protocol.
Right. Cisco developed EIGRP to fix those slow convergence problems that RIP had. It made it much, much faster.
And finally, that brings us to the link state protocols. That's where OSPF lives. And these really changed the game. They moved away from just trusting your neighbor and said, no, we're going to build a complete map of the entire network.
And the whole reason for that evolution is centered on one word, the metric.
The metric.
The metric is the number that measures how good a path is. And the rule is simple. The lowest metric wins.
So what was RIP's metric? And why was it so bad?
RIPv2 uses the simplest metric you can imagine, hop count. It's just the number of routers between you and the destination.
Simple, yeah. But incredibly stupid when you think about modern networks.
Precisely. Because if you only count hops, you can make some truly awful routing decisions.
Yeah.
In contrast, OSPF uses cost.
Cost.
And OSPF's cost is derived from the link's actual bandwidth. So a high bandwidth link, like gigabit Ethernet, gets a very low cost. A slow link, like an old serial line, gets a really high cost.
Right. And EIGRP is sort of in the middle, uses a more complex calculation with bandwidth and delay. But let's really zoom in on that hop count failure, because the example in the source material makes it so clear.
It's the perfect illustration. Imagine you're a router. You need to send traffic somewhere. You have two options.
Okay.
Path 1 is a single hop away, just one router, but it's over a really, really slow 1544 kilobit per second serial link.
Ancient technology.
Basically. Path 2 is 2 hops away, so 2 routers, but both of those links are super fast gigabit Ethernet.
So if we're running RIP, it just looks at the hop count. 1 is less than 2.
Yep.
So RIP makes the disastrous choice to send all the traffic down that slow, ancient serial link, just because it's shorter, gives up all that performance.
And that's just not acceptable today. This is why OSPF is king, because OSPF's metric, the cost, is tied to speed. That 2-hop gigabit path will have a much, much lower total cost than the single-hop serial link.
So OSPF correctly picks the faster path, even though it's one more router away.
Exactly. Better metrics lead to better network performance. End of story.
That distinction right there, moving from just trusting your neighbor's summary, which is distance vector, to building your own precise high-def map link state. That's what OSPF is all about. So let's transition into that core philosophy.
The philosophy is basically share all the ingredients and let every router bake its own cake.
I like that.
Routers don't just exchange directions, they exchange the fundamental data points about the entire network. Every router, every link, every IP address, and, its current status.
And that little data point, that ingredient, has a specific name in OSPF.
It does. It's a link state advertisement, or LSA. You can think of an LSA as a single entry on a shared digital whiteboard. It says, hey, I'm router A. I have an interface on this subnet, and its cost is 1.
Okay.
And the entire collection of all those LSAs that a router knows about, that's its link state database, the LSDB.
So the goal isn't just for routers to talk to each other. The goal is total, perfect synchronization of that database.
Exactly. The whole OSPF process is built around making sure every single router in the area has an identical copy of the LSDB in its memory. If your database doesn't match mine, we have a big problem.
So how does a router go from being plugged in, totally fresh, to having this synchronized global map? The sources break it down into 3 basic phases.
Phase 1 is becoming neighbors. And this starts with just sending out OSPF hello messages.
Just saying hello.
Yeah, they send them out every few seconds to a special multicast address, 224.E0.0.5, to find any other OSPF routers on the same link. They check things like subnet masks, timers, make sure they're compatible.
And once they hear a hello back and confirm, everything matches up.
They hit the two-way state, they've acknowledged each other, they are officially neighbors.
But just because you're neighbors doesn't mean you're going to share your whole map, right?
Yeah.
That's phase 2, exchanging databases.
That's the key. And this phase is really smart. They don't just dump their huge databases on each other. That would be so inefficient. Instead, they use something called database description packets, or BD packets. DD packets.
Think of a DD packet as just a checklist. It's a table of contents of all the LSAs a router has.
So router A sends its checklist over to router B. What happens then?
Router B looks at that checklist, compares it to its own LSDB, and figures out exactly which LSAs it's missing. Then it specifically asks for only those missing pieces.
So it's a targeted request.
A very targeted request. The actual LSA data comes back inside link state update packets, or LSUs. And once that whole exchange is done and their LSDBs are perfectly synchronized, they hit the full state.
Okay, now they're what's called adjacent. And they're ready for phase 3.
Phase 3 is the whole point of this exercise, adding the best routes.
This is where the magic happens.
This is the moment the machine runs. You take that perfectly synchronized LSDB as your input, and the actual entries in your routing table are the output. The router processes its global map using the Dijkstra shortest path first algorithm, SPF.
And that algorithm just crunches the numbers and figures out the best paths. It builds a tree, basically. A tree of the best possible paths from its own perspective. It figures out the subnet, the mask, the next hop IP, everything it needs.
It's amazing that this just happens independently on every single router, just based on that shared data.
Yeah.
So how does SPF use the cost metric to find that shortest path?
It calculates the metric for any path as the sum of the OSPF interface costs for all of the outgoing interfaces in that path.
Outgoing only.
Outgoing only. This is a key detail. The cost to get to you doesn't matter. Only the cost to leave you and the cost of all the next links down the line. So SPF looks at that whole global map and just calculates the total cost for every single possible route. Mathematically, it finds the one with the lowest cost, and that's the winner. That's what gets put in the IP routing table.
Now that we get the logic, let's talk about making this scale. Let's start with a network like Ethernet. If you have, say, 50 routers all plugged into one big switch, OSPF can't have all 50 talking to the other 49, can it?
Oh, that would be an absolute disaster. A complete flood of LSA packets. It's what's called an N-squared problem, and it would crush the CPUs.
So how does OSPF solve that?
It solves it by electing a designated router, a DR, and a backup designated router, a BDR, on those kinds of networks.
So the DR is like the class president, the coordinator.
Exactly. It turns that chaotic many-to-many mess into an efficient one-to-many relationship. The DR is in charge of managing the LSA flooding for that segment. If any router has new info, it only tells the DR.
And the DR tells everyone else.
The DR takes responsibility for multicasting that update out to all the other routers.
And this is where those two special multicast addresses that we mentioned earlier become so important.
They really show how elegant the design is. If a normal router, a D-router, needs to send an update, it sends it to the address 224.0.0.6,
which means
all designated routers. So both the DR and the BDR get the update instantly. This keeps that BDR perfectly in sync, ready to take over if the DR fails.
And then the DR, when it sends the update out to everybody else on that segment, it uses the other address.
Correct. It sends it to 224.0.5, which means all OSPF routers. The DR handles the distribution, and it just simplifies everything.
And this whole DR and BDR election, it actually affects those neighbor states we talked about, the two-way and the full state.
It creates a really important technical distinction. All the routers that see each other's hellos and are compatible, they reach the two-way state. They're neighbors.
Yep.
But a router that is not the DR or the BDR, a D-router, will only form a full adjacency, meaning the full database exchange with the DR and the BDR.
So what state does it stay in with the other D-routers?
It stays in the two-way state with them. It acknowledges they exist, but it doesn't do the full intensive database swap.
Oh, okay. So a full state means I'm sharing my whole map with you. And if you're a D-router, you don't need to share your map with another D-router because you're both just talking to the DR.
It prevents redundant work. It's pure efficiency.
Speaking of scaling, the biggest tool OSPF has for massive networks is areas. For smaller networks, sure, one area is fine. But for huge global networks, you have to create boundaries.
Areas are the main way you scale OSPF. The whole idea is to limit the scope of that super detailed LSDB. Routers only maintain the full exhaustive map for the specific area they live in.
And why is limiting the size of that database so important?
It's all about the CPU. Remember that SPF calculation? It has to run on the entire LSDB. If that database has 10,000 links in it, that calculation is computationally huge.
Yeah.
But if you can restrict the LSDB to just the, say, 500 links in your local area 1, the CPU overhead is tiny in comparison. It also contains failures. If a link flaps in area 2, only the routers in area 2 have to rerun that big SPF calculation.
That makes so much sense. And all these different areas have to connect back to a central nervous system, right? Area 0, the backbone.
And the router that does that connecting is the area border router, or ABR. An ABR is special because it sits in multiple areas at once. It'll have interfaces in area 0 and also, say, area 51.
And its job is to translate between them.
Its job is to summarize. It takes all the detailed information from one area and creates a much simpler, summarized version before injecting it into another area.
And what's the LSA type it uses for that summary?
It uses the summary LSA, which is a Type 3 LSA. The ABR sends these Type 3 LSAs into Area 0, and then Area 0 distributes them to all the other areas. So a router in Area 51 knows how to reach a subnet in Area 10, but it doesn't need to know every single little link and router detail inside Area 10.
So to quickly recap the main internal LSAs, you have the router LSA, the Type 1, which describes the router itself.
Yep.
Then the network LSA, Type 2, which is made by the DR to represent the whole Ethernet segment.
Right, as a single node.
Those two build the detailed map inside an area, and the Type 3 is what the ABR uses to summarize that map for everybody else.
That is the elegant, scalable structure of OSPF. It's modular, it's intelligent. So as you go forward and think about this, remember the key takeaways. OSPF is superior because it uses a sophisticated bandwidth-based metric called cost. It relies on a perfectly synchronized map, the LSDB, that it achieves through things like the DRBDR election. And finally, it uses that powerful Dijkstra SPF algorithm so every router can independently and correctly calculate its own best path.
What's so fascinating is the intelligence that emerges from that. The whole system learns, adapts, and converges, not because a human is telling it what to do, but just based on pure applied mathematics. So we discussed how the OSPF process results in every router having an identical global map of the network, the LSDB. But the SPF calculation itself, that's run locally on each device, which means every single router in the network is constantly independently running a mathematical analysis to find the absolute best path from its own unique perspective to everywhere else. What stands out to you about the power of that independent parallel calculation, where hundreds, maybe thousands of devices are all simultaneously solving the same complex routing problem all on their own? We'll leave you with that thought.